zeros.
Make use of binary, that's true. The fundamental architecture of any system you can think of is binary. Even real-world systems, behavioral systems such as cells, or behavioral systems such as organs, living things, we use a binary system to make decisions. But we don't call it binary, but it takes the same principles. What else did you find out?
So we also discovered that the output of these logic gates can be sketched onto a truth table.
Right? We can also represent logic gate output as truth tables. Quite true. So I can say everyone has an understanding of logic tables now. True. Did anyone find any issues when they're doing their research? Did anyone encounter any issues? Okay, so if there are no issues, let us begin. So today we're going to be looking at logic gates, and once we're done with our theory, to add on to the research work that we currently did in the morning, we're just going to run a few exercises on systems design. So when we're talking about logic gates, we're saying these are the basic building blocks of any architecture that we know out there. They allow us to represent what we call digital circuiting within our computer architecture design. So at the end of the day, we can represent data processing within a circuit by controlling how data moves from one node to the next. And at the same time, we can also determine the type of output that is going to be outputted by our gate, as well as the type of input that it is going to take. And the output that a gate outputs is greatly dependent upon the type of input that the gate takes. I'm sure you've seen from your research that in most cases, or in most instances, an inverse relationship can exist between input and output, where, for example, if the output is false, somewhat the inverse relationship is true, the input is true. So we realize that when we have this understanding of basic input-output relationships, we can then model a specific system to produce a specific output that we wanted to produce. And we're also saying, when we're looking at the basic states of a digital circuit, basic states of a digital circuit are either it is in high, usually represented by your positive voltage, or represented by a 1, or it is in low, represented by a low voltage, or represented by a 0. So you then realize that as the transistor circuits move current within a computer, they exist within these two states, a state that is high or a state that is low. And we can then translate these two states to represent our binary. So we can then also go on to argue and say, when we're looking at a logic gate, the output can be either of these two states. The output of any gate can either be high or low. For example, we can have two input types which are high, for example, a 1 and a 1, and the output type can be a 1. Or we can have two input types that are of low count. For example, we can have a 0, and the output type is going to be a 0. So depending on the type of gate you're using, you can also affect the type of output that you are going to have at the end of the day. Is it making sense, ladies and gentlemen, so far?
Yes, sir.
So when we're looking at our logic gates, there are 7 types of logic gates. Can we quickly name the 7 types of logic gates that we found out during our research? Or better yet, let me start off by naming the AND, the OR, the XOR, the NAND, what else? What are the you think exists out there? Yes, Prince?
Not gate.
The NOT gate. What other gate exists out there?
The XNO.
We've already stated the O.
We have the NAND gate, say.
I already stated the NAND. What other gates exist out there, ladies and gentlemen?
Hello, sir.
Yes, hello?
There's the NOR gate.
It's like the third time somebody has mentioned that, but we've already mentioned the gate.
Buffer gate, sir.
The buffer that I would take. What else?
There's the XNO.
There's also the XNO. Yes, that's quite true. So, when we're looking at logic gates, the 7 logic gates that you stated, your responses, are the derivative gates that come from the 3 basic types of logic gates. And the 3 basic types of logic gates are your AND, your OR, and your NOT. So every other gate, either is the NAND, it's the XOR, it's the NOR, etc., they come from these 3 basic constructs. And we're going to start off by looking at these 3 basic constructs so that we understand how every other gate is a derivative from these 3 basic constructs. So let us start off with the AND gate. This is the insignia for the AND gate. It is like person that is lying on their side, or a D that has 3 points. The first 2 points that you see on your D are your input points. So it has 2 input values that you can accept, or it has 2 A and B values that you can accept. And the output value is singular, which is your Q. So an AND gate by nature functions in such a way that if the values of either one of these inputs is false, the output also then becomes false. If one value is true, for example, right now, our switch is on, so our value is true, the output still remains false. So if you want to have a true output in your AND gate, exclusively all input values should be true. Does that make sense, ladies and gentlemen?
Yes, sir.
Yes, sir.
So any composite inputs of ones and zeros, either a 0 here and a 1 there, will still result in a false on your output. If you want an output that is true, input 1, which is your A, should be true, and input 2, which is your B, should also be true. Next, we have what is known as the OR gate, right? And when we're looking at the OR gate, we're saying it also has 2 inputs, and it also has 1 output. If at least one of these inputs is true, then the output will also be true. So if neither input is a 1, it means that the output will always remain 0. So neither input is a 1, so our output remains 0. But if one input is a 1, the output in itself becomes a 1. If both inputs are a 1, the output becomes a 1. If both inputs are then a 0, it means that the output in itself also becomes a 0. Is anyone lost? Okay. Now we move on to the NOT gate. This gate is usually known as an inverter, mainly because the output is the exact opposite of the input. So the role of this gate is to invert the input. And when we look at the gate, it has a maximum of 1 input. And the only states that the gate can take in terms of output are 1 and 0. So it only has 2 states. And by this, we mean when your input, for example, is a 0, it means that your output is going to be a 1. And alternatively, if your input is a 1, your output is going to be 0. So you realize that the NOT gate inverts the input within the circuit. So for example, right now, the switch is off, but the light is on, right? And we're saying we can then decide to put the switch on and the light will then turn off. Do we understand, ladies and gentlemen?
Yes.
Sir.
Yes,
Yes,
sir.
sir.
Right. So, now that we know our basic foundation, we can also think in terms of binary relation. And when we think in terms of binary, we are then saying a high input is your plus,
Yes, sir.
and the low input is your minus. And we go on to say a high input or a positive can also be recorded as a yes, and the low or negative input can be recorded as a what?
No.
A no.
Can be recorded as a no. Quite true. And we can go on to say a high input, a yes, and a positive can be recorded as a true, and a no, low, or negative can be recorded as your false. And ultimately, your positive, your high, your yes, your true is your 1, and your negative, your low, your no, your false becomes a 0. Is anyone lost this far? Right. So, let us look. Let us look at the AND gate. And within our AND gate, we have 2 input values. And our input values are our A and B. And we have 1 output value, and the output value is Q. So, if we are then going to construct a truth table for our AND gate, means that we have our A, our B, and ultimately we should have our Q. So, if our A is 0 and our B is 0, our output is 0. If our A is false, our B is false, the output value also becomes false. If our A is false, our B is true, what becomes the output value?
It becomes false.
Zero.
Indeed, it becomes false. And can someone explain why it becomes false?
Say because it's an AND gate. For an AND gate, you say it's either like we have 2 positive inputs for us to have a positive output.
Right. So we need to have 2 positive inputs for us to have a positive output. That's quite correct, Richard. You need to be able to have 2 positive input values on your A and B for you to have your positive output. So alternatively, if your A is positive and your B is negative, still the output value is going to be negative. So if you want to have positive outcome, we need to have 2 positive inputs. Easy stuff, right? Let us now move on to the OR gate. And again, we have our inputs. And we also have our output. And when we construct our truth table, we look at the values of A, B, so that we have Q. So if your A is 0 and your B is 0, your output becomes 0. If your A is 0, your B is 1, your output becomes what?
It becomes
1.
1.
1.
It becomes 1 because we said when we're looking at the OR gate, either one of the inputs needs to be true in order for the output to be true. So also when you have a 1 on the A node, a 0 on the B node, the output still is going to be 1. And when you also have a 1 on your A, a 1 on your B, the output is also going to be 1. Let us now look at the NOT gate. When we're looking at the NOT gate, we're saying there's only one input and one output. And the truth table takes an inverse type relation. The relationship between A and B is of inverse nature. So if we have a 0 for A, the output is going to be a 1. If we have a 1 for A, the output is going to be a 0. Is anyone lost? So, when we did our research in the morning and we looked at combining logical gates, what did we find out?
We found out that if you combine the AND gate with the NOT gate, we find NAND gate.
Hello, sir.
Combine the AND gate, yes?
Okay, if we combine an AND gate and a NOT gate, we get a NAND gate.
Okay. So basic configuration states that the inputs of your AND affect the input of your NOT, which affects the output of the whole equation. So for example, if we have our A and B, we need to produce C, which results in Q. So when we construct the truth table, first we look at the values of A and B that produce C. And we now look at the input of the NOT, which is our C. Okay. So we replay our A's and B's, produce our C for all the layers. Now we look at our Q, and we're saying the input determines the output, and the input of our NOT gate is our C. Therefore, if something is not false, it is what?
True.
It's true. And for the next level, the output becomes what?
1.
For the third level, the output becomes what?
True.
False.
True.
And for the last level, the output becomes what?
0.
False.
The output indeed becomes false. Is anyone lost? Do we have anyone who's left behind before we proceed? So basically, when we're looking at the output of Q, we are saying Q is the NOT of A and B. Q is the NOT of A and B. The result that we get by looking at A and B, the opposite of that result is your Q. So Q is not A and B. 1 is not 0 and 0. 1 is not 0 and 1. 1 is not 1 and 0. 0 is not 1 and 1. Does that make sense?
Yes, sir.
So, when we're then looking at digital circuits, the diagram that you have in front of you is a typical example of a digital circuit that we can have in a computerized board. For example, a basic cell phone or a basic computer has a layered architecture of these gates working together to achieve a specified outcome. And you realize that whenever we are then running these experiments, we need to also then check to see how our logic is progressing within a series of laws, so that at the end of the day, we have something that is signifying true intent. So now I want us to run a simple demonstration. We just share my screen with you. Right. So can everyone see the screen?
Yes, sir.
Yes. Yes, sir.
Yes.
So let us look at a basic example we did a few minutes ago. Let's call this a switch. And also need another one. Let's also call this a switch. And we need and the gates. And we need output. So the value of this switch is now true. The value of that switch is now true. Therefore, the output is also what?
It's also true.
True, sir.
It is
Yeah.
also
True. We also talked about the NOT gates. And we're saying, for example, if we have our NOT gate placed there in our circuit, and we have our bulb placed there, what do you think is going to be the output when we close this circuit?
False.
false. False.
Output is going to be false. And then we take our NOT gates, place it there, place another bulb there. What is going to be the output when we combine or close
True.
this circuit?
True.
Can someone explain why the middle bulb is still lighting?
Hello, sir.
Yes.
I want to try. Okay, the bulb. Okay, sir. The bulb is the bulb lights because the note gate shows the inverse of the output. So when we join the second bulb, it also lights because at first we got an output of 0. So when we connected the last bulb, it causes the second bulb to light up because it converts that 0 to 1.
Right. So when we put the NOT gate on the output of the AND gate, it converts the 0 to the 1 because our input currently is 0, 1. Do we understand Miriam's example, Miriam's explanation?
Yes, sir.
Yes, sir.
Is anyone lost at the moment? Okay, seems everyone understands. Right. Let us now move on to the other gates. Let us look at the NAND gate, right? With our two inputs there there, what is going to be the output?
True.
The output is going to be true. Do you want to explain why?
Yes, sir. We have inputs. Those are switches, which is on and off and on. So that will be a 0 and a 1. A 0 and a 1 through an AND gate. Sorry, an NAND gate. It will turn to true.
Do you understand this explanation? Yes.
Hello, sir.
No,
Can
sir.
try.
Munashe, please go ahead. Your hand is up.
Okay, sir. So
I think,
a NAND gate is
okay.
We seem to have lost you there. Can you come again?
Okay, I think NAT gate is the inverse of AND gate. So when we have a 0, it means that it is going to be a 1. So if we have two inputs, like 1 and 0, or on and off, this means it is true. If A of AND gate,
Right. Elias, your hand is up.
I just wanted to explain on the land piece, but it's not like Chadu has already explained.
Right, I'm back. My network get phased out. Elias, you wanted to say something, your hand was up, and then Richard, you can follow thereafter.
I wanted to say the NAND gate is an opposite, is a combination of and NOT gate. So at first we have the AND gate, which we have an output of 0, which is false, and then we follow by a NOT gate, which we have an output of true, because it will turn the false into a true.
Okay. Richard, your hand was up.
Okay, say to add on what other guys were saying, an AND gate is a combination of two gates, an AND gate and a NOT gate. So whatever an output for AND, that would be an input for NOT gate. So it becomes an inverse.
Okay. Right, let us move on. I think we understand our NAND. Let's remove that. So now we're going to look at the XOR. And remember, we said with an OR gate, we look at both inputs. If both inputs are positive, what becomes the output?
It will be true.
Positive also.
May you come again, sir?
I'm saying with an OR gate, if both inputs are positive, what is the output?
It will be positive, sir.
Gate. And we have both our inputs as positive. What is the output? The output is positive, right? Or the output is true. And I am then saying, if we then take the same input into an XOR gate, what becomes our output?
False.
And may you please explain why the output is going to be false? Richard, go ahead. Yes, hello?
In the exclusive OR gate,
Okay,
if
say
both
for
the
an
inputs
XOR gate
are
for it to
positive,
become
the output will.
okay. Say I was saying for an XOR gate for it to have a positive output, you say that like their inputs need to be different. So say that false or true for us to get a true output.
So one of the inputs needs to be false in order for us to get a true output.
Yes, sir.
Is this making sense, ladies and gentlemen?
Yes, sir.
Yes, sir.
Right. Let us look at the NOR gate. And we're saying that the NOR gate is just like your NAND gate, but it's an AND gate that is usually followed by a NOT gate, right? So when we look at the input-output relationship, we're saying, again, if the input contains any form of positive, either in the first node or the second node, the output is generally going to be a false. And if the input contains a double false, the output is generally going to be positive. Right? For example, as you see on screen, both inputs are false. And the output is what? True. If one input becomes true, the output becomes false. If both inputs become true, the output still remains as false. Does that make sense, ladies and gentlemen?
Yes, sir.
Yes, sir.
Loveridge, your hand was up. Wanted to say something?
I needed to explain how the NOR gate works. Then somebody explained it.
Okay. So does anyone have a question with regards to the gates we have done so far?
Say, can you explain why the NOR gate turns on when all inputs are false?
Can you explain why the NOR gate turns on when both switches are false? Right. Let me just do something over here. Let's delete that. That. Right. So, what makes up a NOR gate? That's the question you should be asking.
Hello, sir.
Yes, hello?
Okay, a NOR gate is just a combination of a NOT gate and the OR gate.
Right. It's a combination of the NOT gate and the OR gate. Right? So, if our input into our OR gate is negative, what then becomes our output?
It also becomes
0 or
negative.
0. It also becomes negative. And then when we then call the NOT gate and say something that is not negative or negative is not, what becomes the output?
Positive.
Becomes positive.
And now I get it.
Remember, we said we have three basic constructs of these gates, and every other gate is built upon the three fundamental constructs. For example, when you take these two and you combine them to two, you then get a new construct. Do you understand? So this symbol that I've just put, the NOR gate, is a combination of your OR gate and your NOT gate. Is anyone still lost? Okay. Now we look at our buffer. Initially, when I was asking for all the gates, somebody mentioned that there's something called a buffer gate. Do you want to explain what a buffer gate does?
Say I can try. The buffer gate, I mean, it combines all the three major logic gates, which is AND, OR, and NOT.
So what does that mean? In simpler terms.
Combined logic gates.
And my question again is, what does that mean in simpler terms? Nasha, do you want to assist?
I wanted to add on the buffer gate.
Go ahead.
Okay, so basically the buffer gates, when all the inputs are negative, the output will be positive. And when all the inputs are positive, the output will be positive as well.
Are you sure about that?
Okay. So I also want to just give it a try.
Mm-hmm.
Okay. I think a buffer gate. It only has one input, then also one output. So when the input is 1, the output will be 1. When the input is 0, then also the output will be 0. Simultaneously, when the input is true, the output is true. When the input is false, then the output is also false.
And why? What is the reason behind that? In simple terms, say you're teaching a grade 5 class. How would you explain the buffer to them?
But
Hello, sir.
Yes.
I think since there is a single input, there also has to be a single output. So if input is positive, then consequently the output is going to be positive as well.
If you look at the NOT gate, for example, it also has a single input and a single output. But the difference is that if the input is negative in the NOT, output is positive. Whereas in the buffer, if the input is negative, the output is negative.
Say, I want
Why?
to try again.
Okay.
So a buffer gate takes any input and compares the value to 0. I hope this is now simple.
I don't understand. Please explain further.
Okay, if the input signal is 0, the output will be 0. If the input is non-zero, that is, it's 1, the output will be a 1.
So what
So
does
far,
that
that's what I
tell
know.
us? Getting to the core of the issue. Elias, your background noise is too much. Can you type your response instead? Sean, your hand is up.
It tells that the input is the same as the output.
Tells us that the input is the same. Does nothing to the input. It comes in and goes out as it is. That's what I'm looking for. Zero input results in zero output. One input results in one output. There is no conversion process that is executed by the buffer. We can use the buffer when we want to extend circuits. For example, we can just say, let's see if this works. See, if we decide to switch this off, it also goes off. So we can use it to extend our circuits, our circuitry, because it does absolutely nothing to our input signal. It maintains it as it should be and outputs it as it came in. Are we still together?
Yes, sir.
So,
Yes, sir.
I'd also asked you to look at designing systems using logic gates, and asked you to look at the traffic control system, right? And what output did you have? Let us just delete all this so that we have numbers to work on. All right. So here are our three outputs. Let's call this the red light. Then we call this amber, and we call this our green. So it's red, amber, and green. Right. So how did you design your circuit? Are we still together?
Yes.
Yes. Maliwa, Dishe, what did you do to solve the problem of the traffic system? Seems Ndisha doesn't want to respond. Go code decide. What sort of circuitry did you design? Right. I'm sure everyone now has access to this Jamboard. Can you show us the circuit that you drew? Or better yet, let's do this to represent our red. Then we know the second one is our amber. And the last one comes our green. And we know flow of sequence is 1, 3, and 2. This is our flow of sequence. Right. More Blessing says NAND. That's not answering the question. Where do you place it? How do you join it, etc.? That's what I want to see. I asked you to design a circuit, so you need to show me you designed the circuit.
Say, can I try?
The Jamboard is open. You can draw.
Say not to draw, but I just wanted to say that when I'm designing my switch, I can use resistors. A resistor is a flow
I want you
amplifier.
to draw. I want you to draw insignias that we need everything in between. So that we can all learn.
Hello, sir.
Yes, hello?
In say I'm failing to be able to draw, but I drawn it through my book. Can I send it?
We will send it away. You put it in the Jamboard. That's why we have the Jamboard. Select picture, right here, add an image, and then you can add your picture.
Select pick number.
That's how you learn. You won't learn properly, so are you done?
Not yet, see.
You see this icon, you can add image. Click on the icon, select the image from a location, and then press OK, and the image will pop up. It will see you. So as he works on uploading his image, anyone else? Someone says they cannot edit. Let's see.
Let us see.
I don't see any restrictions. Are you using your CUZ email?
See.
Are we still together?
So it's saying that you have to allow us to use.
Let us try another board. Right, I think can you try and edit those that were saying they didn't have access? And where are we? So you're telling me that in a class of 200 people, only one person attempted the exercise?
Hello, sir. I have a
Hello.
solution, but I don't have the Jamboard. So can I send it to someone and then he or she can draw it and then I'll explain.
I didn't even get what you're saying. What are you saying?
Well, I said I have the solution. I have a solution to the problem, for the robot, isn't? But then I do not have Jamboard, the Jamboard app. So can I send it to someone and then they can draw and then I'll explain.
What do you think you should do?
Okay.
So when you send your solution to someone, they didn't finally draw the solution, please inform us so that we can go back to it and see what is what. Other than that, let us move on. So now we're going to look at the concept of internal memory. And as part of your reading for the week, you can go on and look into the extra resources, that is your YouTube videos attached on this description, as well as within the given textbook. It's in chapter 5, items 5.1 and items 5.3. Before we proceed with the lecture, please switch off your mics. Next person to switch on their mic and disturb the lecture will be voted out of the meeting. So, when we're talking about computer architecture and computer memory, we are saying that whenever we are representing a computer, so a computerized device, a computerized device exists within the stable or unstable state. So you realize that within the stable state, a computer is capable of representing information by writing to memory, and within the unstable state, a computer is not capable of representing information, neither is it capable of writing information to memory. So within this lecture, we're going to look at how we write to memory at least once, and how we write to memory multiple times. So in essence, we're going to look at the memory operations of a computer, namely the types of memory that a computer uses or utilizes to write to data, to memory, and the type of memory that we would prefer to use in any computing situation. So most memories that we have within a computerized system are of semiconductor type. And when we're talking about semiconductor memory, we're mainly talking about the 6 major forms of memory, which are your random access memory, read-only memory, your programmable read-only memory, erasable programmable read-only memory, your electronically erasable programmable read-only memory, as well as your flash memory. So you see that each one of these memory types has its own advantages. And that's what we want to leverage on when we create an architecture for a computer. You want to be able to have that operational efficiency so that when we want to write to memory within any instance, we can do so without causing any instability within our computer system. So we're going to take a look at the various types of memory, including the advantages, disadvantages, and how we can overcome these advantages and disadvantages. So let us start off with the first type of memory. The first type of memory is known as your random access memory. So when we looked at the basic structure of a computer, when we're looking at the Harvard machines, when we're looking at the Turing machine, we sort of briefly looked at memory addressing as well as memory access. And can someone recall what we said when we're talking about memory when it comes to the Turing machine? Anyone who recalls memory of the Turing machine? Right?
Say I can try.
Sure.
Okay, it shows us the old state memory and then the new state as it moves from the right to the left on the Turing machine.
You then realize that memory can be of old state, memory can be of new state. Memory of old state is your old data, whereas memory of new state is the new data which you have written onto the memory block. As well as memory becomes a series of bytes. And that contribution is coming from Adana. It says that memory is a series of bytes and is actually true. If you look at the arrangement of data within a computer, significantly it's within the forms of zeros and ones. And as those zeros and ones become huge in size, they are stored as bytes on memory cells within a computer. And these bytes have some form of addressing so that it is easier for the computer to make reference to the data and retrieve this information with optimum speed. So when we're talking about random access memory, we're saying we want to allow a computer to read and write at byte level. We want to allow a computer to read and write data at byte level, not at bit level. Capability to read and write data at byte level allows for faster processing. It allows for faster retrieval of memory. It allows for faster retrieval of instructions. Are we still together, ladies and gentlemen?
Yes, sir.
So, because of this, we have two significant types. So we have two significant types of random access memory, namely the static RAM as well as the dynamic RAM. Any idea what the static RAM does and any idea what the dynamic RAM does?
Say
I'm sure
static
you did this in
RAM
your
is
first year.
volatile. A static RAM is volatile, whilst a dynamic RAM is non-volatile.
And what does that mean?
Yes, sir. Volatile means that when the computer is switched off, the information is erased, and non-volatile means that it's not erased when the computer is switched off.
Sorry, I didn't get that. My network had done something to your mic. You please come again.
Okay. Volatile means that the information is erased, removed when the computer switches off, and non-volatile means it remains there even when the computer has turned off.
Right. So RAM is highly volatile. And to a greater extent, it requires some form of conduction or power or electricity to maintain specific aspects of memory. We want to be in a state to use the RAM, but we also want to be in a state to save or store the files or data that we would have written to our RAM, which is why in most cases, when your computer runs out of power, for example, the system state is stored in your RAM, such that when you when you charge your computer and you switch your computer back on, the programs that you're working on are saved in memory. And that is an example of which type of RAM. Hello, class, are we still together?
Yes, sir.
My question was looking at the functionality that you come across every day on your personal computer. Now, saying if you look at your personal computer, if it runs out of power, the system state is saved, whether you're typing a document that is already saved to memory, or you're working on your browser, etc. And we're saying, what sort of RAM has the capability to maintain the system state even after power outage?
Isn't it dynamic RAM, sir?
Right. It's your dynamic RAM. Dynamic RAM has the capability to store your data. It stores this data in what we call an integrated circuit. For example, if you look at your basic computer, it has what they call RAM chip memory in some instances. And that is your basic integrated chip. It has the capability to store bits of data within the chip, such that when you then want to access this data, the data is accessed directly from your RAM rather than calling the data from your hard drive. Is that making sense?
Yes, sir.
Does anyone have a question?
Hello, so I have a question.
Go ahead.
From a laptop, they say this laptop is 4 gig RAM. So which type of RAM is it? Is it static or is dynamic?
They say on your laptop there is 4 gig RAM. And your question is it static or dynamic? All right. Before I answer your question, can I ask you 2 questions of my own?
Okay, sir.
Yes, sir.
My first question, is that RAM capable of storing data?
I'm not sure, sir. That's why I was asking.
Sorry?
I'm not really sure.
What do you think as a student who's doing implement IT for the past 2 years? What
That's
is your
why I
point
was
of view?
asking for clarity.
And that's why I'm asking you, because
I
you
think
already have an answer. Your
I
question.
think it stores data, sir.
Stores data. And the fact that it stores data in an integrated circuit makes it what?
A dynamic RAM.
Well done. Can you give him a round of applause? So you only needed to make inference of the definitions of RAM that we have. For example, if I see the video that's actually playing on your screen, it shows 2 types of RAM. Dynamic RAM. The one on top is the one that you usually find in your desktop computers. These black items that you see are what we call the circuit. If you check behind it, it actually gives you those gold pins that are printed onto the circuit, and as well as the circuiting in terms of the grid lines that show what data item goes where. So this is an example of dynamic RAM found in a desktop computer. And this is an example of dynamic RAM found in your laptop. And this specific version of dynamic RAM is called DDR2. And I know now they have DDR4, DDR5. Basic difference is the architecture, basic difference is the size of the particular capacity of the RAM. Are we still together?
Yes, sir.
Yes, sir.
Right. Now we move on to read-only memory, also known as a ROM. And we're saying with read-only memory, these can be erased for programming, but might have the requirements such as the need for ultraviolet light, or the need to ensure that only the ROM is writable within a particular block. And in most cases, we need special equipment to make sure that we write onto the ROM. And a very good example of a ROM that you can think of is magnetic tape, is floppy disk, it's your CD, it's your DVD, it's your internal memory chip, etc. These can be programmed using special equipment, or these can be programmed using ultraviolet light. If you check on some of your laptops, for example, your laptops have a CD-ROM that allows you to actually write on a CD. It's a very good example of these ROMs that I'm sure you've come across at least once when you opened a computer or opened an electrical device. Include, for example, these chips that you see playing on my video. Notice how they have multiple pins that allow the chips to be placed in a specific programming unit, and the specific programming unit then writes onto the chip. So for example, these pins, for example, that you see, are barely visible, show how you connect it to a circuit board and how you write to it. And these are examples of read-only memory. As for the CD, I'm sure everyone has seen a CD before. You'll not be showing you CDs in 2021. Would rather talk about, for example, virtualization. Now let us look at the types of read-only memory. So we have 5 major types: EEPROM, EEPROM, custom ROMs, OT-PROMs, as well as flash. And we're saying, when we're looking at our ROM uses, again, the biggest advantage of ROM is that it defeats the volatility issues of the RAM. It becomes non-volatile. So I was saying, one big advantage of the ROM is it overcomes the issues of volatility. In most instances, when you write data onto the ROM, the data is written onto permanently, and that allows you to permanently store your data. And when we look at it from a programming perspective, we're then saying it is advantageous because you don't necessarily then need to constantly make sure that your information is stored, because it will already be available and it will already be permanent. So some examples where we use ROMs include in microprogramming, storing library subroutines, example on hardware, in storing your system's programs, for example, your BIOS, in storing function tables. For example, if you look at your Ethernet card, it also has custom ROMs built onto it, and then also saving embedded systems. For example, those computers that are used for specialized duties, they will then have ROMs that have embedded systems written onto it. And if you want to make your computer better, you need to buy a new ROM and insert the new ROM onto the computer. A very good example where this is actually achieved is in computers that use graphic cards that have embedded systems on them. Does anyone have a question with regards to your role? Anyone with a question with regards to the ROM? Okay. Let us now move on to the EPROM. So, when we're looking at the EPROM, we're saying this is memory that can only be written to with a programmer. The programmer is responsible for rewriting instructions within your ROM. It is usually erasable through the use of ultraviolet light, and it is non-volatile storage that does not require any form of electrical conduction to be stored. The biggest disadvantage is that whenever you want to write to an EPROM, you first need to erase it. You run an erase function that deletes the data on the EPROM byte by byte. Only then, when all the data has been erased, can you write back onto it. You can also take a look at the cost implication, how the EPROM is, up till today, one of the most expensive types of ROM that we have in the contemporary world. And thirdly, you need specialist devices to be able to write to the memory. And a very good example where such ROMs work is, for example, within commercial devices such as video cameras that record to Blu-ray, or video cameras that record to the MMC disc. We can take a look at things such as CD writers or DVD writers that record DVDs, especially if you're burning your DVD in what we call an open format that allows you to add more information and delete the DVD. The usage of the ultraviolet light erases the optical characters that would have been written onto the disc and allows you to write new optical characters. Are we still together, ladies and gentlemen?
Yes.
Yes.
Yes, sir.
So, what I want you to go and do with regards to your homework for the week, I'm going to put up a link on our Moodle platform, and we are going to submit our traffic light logic gates design on the Moodle platform. And secondly, I'm going to put up the presentations, both for the logic gates and this one that is currently on screen. And you're also going to look at the presentations, write your own personal notes, and complete the rest of the presentations. So that when we meet next week, we're going to begin our discussion on dynamic RAM architecture. Do we have any questions? Hello, class.
Hello, sir.
Mhm.
Hello, sir.
Hello.
When are we submitting our traffic light?
Today before 6 o'clock.
Okay, sir.
Are you answered?
Say, are we going to submit it as a picture or we are going to draw on the Moodle platform?
What do you think?
For me, I'm not yet technologically sharp. A picture would be great for me, say.
You need to be technologically sharp because this is a BBM and IT program.
Okay, say. But it was just for today.
Right? So the link is up. You can check with Moodle. Does anyone have a question with regards to the instructions or with regards to anything that we have done?
Say, some of us are on the module, the current modules they are not uploaded. So how can I access the module?
Sorry, can you come again?
I'm saying on the module, on my platform, I don't have the current modules.
What is your reg number?
R20 2709H.
Can you send your reg number on the chat so that I add you to the group? Yes.
9 Tuesday.
What about yours?
I don't have the current module.
You send in your reg number.
Okay, sir.
Simbarashe Bruce, your mic is on, please switch it off.
So also include a summary explanation when you submit your traffic lights. And you can use Microsoft Word diagrams or Visio or Microsoft Word flowchart diagrams to submit your file. Or alternatively, you can go to Logic, .ly and create a diagram there. Copy the diagram, paste it in your document, and submit it today by 6 p.m.
Hello, sir.
Hello.
Can I ask you, ku vari suitable, vari vasingazivi IT kudaro, vanenge vachida mapics, can't you just allow us just to send pics for today?
No. I'm not going to allow you to send pics for today.
Okay, say hopefully by 6 our portals will be fixed, our modules will be fixed. But I wanted to ask if it's okay that if our portals are not fixed, then can we send the documents, the Microsoft Word documents, with our traffic on the group chat, on WhatsApp group?
No, cannot. Submission is going to be on Moodle, and I have all your reg numbers here. And I will add you to the group. By the time it is 4 o'clock, you will already be in the group. Any other issues? So if there are no other issues, then we might as well call it a day.